Welcome back to this course on Fundamentals of Computer Architecture. In this and the next lesson, I will show how code can be scheduled to improve its performance on a pipeline processor. The purpose of this lesson is to present the code example and the pipeline assumptions. As usual, in case you want to read the material this lesson is based on, it's based on section 3.2 of the 5th edition of the textbook Computer Architecture, a Quantitative Approach by John Hennessy and David Pedersen. In the previous lesson, we extended the canonical MIPS pipeline to handle multi-cycle operations, operations that require more than a single execution stage. We also saw, however, that longer pipelines suffer from more stalls due to read-after-write hazards. In this lesson, I will discuss what the compiler or you, assembly programmer, can do to avoid such stall cycles. This will be our example throughout this lesson, adding a scalar value s to an array of doubles x consisting of 1000 elements. The C code is a simple for loop. We start with a straightforward translation to MIPS64 assembly. I assume that register R1 contains the base address of x or equivalently the address of x0. I also assume that R2 contains the address of x1000, or in other words, R2 points to the first memory location after the array x, since x999 is the last array element. Finally, I assume that floating point register F2 contains the scalar value s. Every line until now starts with a semicolon. This indicates that it is comment and not actual code. In the first instruction of our for loop, we load xi into floating point register F0. Then we add the scalar s contained in F2 to F0 and store the sum in F4. Then we store the sum back to the address of xi, which is still in register R1. Then we increment R1 with 8 so that it now points to the next element of xi plus 1. We need to increment by 8 because the size of a double is 8 bytes. And then we test if R1 now points to the first memory location after the array x. If it does not, branch not equal, we jump back to the beginning of the for loop. Finally, we have a no-op instruction, a no operation in the branch delay slot. Recall that the instruction in the branch delay slot is always executed whether the branch is taken or not. This completes our simple program. Note that almost every instruction is dependent on the previous instruction, and therefore we can expect a lot of stalls when this code is executed on the multi-cycle pipeline. Throughout this lesson, I will assume the pipeline latency summarized in this table. On this and the following slides, I will briefly describe and explain these latencies in details. If the producing instruction is a floating point ALU and the consuming instruction is also a floating point ALU instruction, then the latency is 3 clock cycles. This is explained by this pipeline execution diagram. The result is not available until the end of the A3 pipeline stage, so even if we forward the result, which we do, the second instruction will occur 3 stall cycles. If the producing instruction is a floating point ALU instruction and the consuming instruction is a store, then the latency will be 2 clock cycles. This is illustrated in this pipeline execution diagram. The store computes the effective address in its execute stage, and the value to be stored, which is the value being computed by the floating point instruction, is not needed until the mem stage and can be forwarded from the A4 stage to the mem stage of the store as indicated by the red arrow. The store therefore only incurs 2 stall cycles. Notice that here I assume that several instructions can be in their mem or write back state simultaneously, while in the previous lesson I assumed this was not allowed. It's a minor detail that should not confuse you. If the producing instruction is a load and the consuming instruction is any instruction except a store, then the latency is 1 clock cycle. This is illustrated in this pipeline execution diagram and corresponds to the by now well-known load use data hazards. On the other hand, if the consuming instruction is a store, then the latency is 0 cycles. This is illustrated in this diagram. Because the value loaded can be forwarded from the mem stage to the load of the load to the mem stage of the store, no stall cycles are required. Finally, when the producing instructions and consuming instructions are both integer instructions, the latency is again 0 clock cycles, because the result can be forwarded from the X stage of the first to the X stage of the second, as this pipeline execution diagram illustrates. And finally, when the producing instruction is an integer instruction and the consuming instruction is a branch, then the latency is 1 clock cycle. This is because we assume that branches take place at the end of the decode stage. Therefore, if a branch depends on the instruction that immediately precedes it, 1 stall cycle is required, so that the result can be forwarded from the X stage of the integer instruction to the decode stage of the branch, as illustrated in the pipeline execution diagram at the bottom. This concludes this lesson. Thanks for watching. In the next lesson, I will show how the code presented in this lesson can be scheduled to reduce the number of stalls. Hope to see you back.